Hello, everybody, and welcome to this year's lecture on quantum computing. Due to the circumstances, we will conduct this lecture or a series of lectures in a slightly different way. So usually we do face-to-face lectures and go through exercises during these lectures and have the chance to discuss everything that I wasn't clear about or everything that needs further elaborations in more detail. However, this year it's different. So what we're going to do is, or what I'm going to do is provide you with these video lectures, so recordings to the modules of this lecture. And then we will also have the chance to go through interactive lectures. So we will use a video conferencing tool such as Skype or Zoom. And here we will have the chance to talk about everything that you want to know more about in more detail. My name is Florian Neukert. I am the Director of Advanced Technologies at Volkswagen Group of America. I work out of San Francisco in California, and right now I think we are all in the same boat. So I'm in shelter in place, and the only things that I'm allowed to do is go out to buy food or go out to record a lecture, as I'm doing now. What that means, so Director of Advanced Technologies, is that I'm leading a group of researchers and engineers that are interested in new technologies, in anything that could help our company become better in what we do, and could help our customers to experience our products better, to basically make things in the world better. I know the last thing that always sounds flat when I say that out of the Silicon Valley, because that's the usual statement that you hear from this place, but we mean it. So things that we're interested in are, of course, quantum computing and how it can help us to improve whatever we do. So let's say we want to improve machine learning algorithms, then that's interesting for us. We want to understand how we can leverage the potential of quantum computers to speed up the training of diverse machine learning algorithms. For example, searching the neural weights, for searching the weights of neural networks, or doing gradient descent in specific training algorithms. That's something you can do. You can reformulate many of the machine learning problems that we're interested in into optimization problems, which are very suitable then for a very special kind of quantum computer, quantum annealing systems, which we will learn more about later. But also materials science is interesting to us. So we want to use one quantum system, the quantum computer, basically to simulate another quantum system, such as molecules, and that helps us to improve, let's say, our battery chemistry or come up with new materials that could be relevant for production. We're also interested in IT security, of course, in cryptography specifically. We all know that today's quantum computers do not pose a threat to encryption algorithms, but in theory they do. So that means, what if someone steals our data today and in 10 years is able of decrypting that data? Is that still a problem? So, and we must say yes, depending on what that data is, it is a problem. So either it's customer sensitive, either it's prototype studies, whatever it is. So it may be still valuable in 10 years. And 10 years, because I mean, this is always the time frame that people give you and that also I would give you. Maybe in 10 years, we will have that perfectly error-corrected quantum computer, gate model quantum computer that poses a threat to current encryption algorithms. We're not there yet, but still we need to start thinking about it. And thinking about it means either look into algorithms, classical algorithms. So anytime I say classical, I mean not quantum. So classical algorithms that can withstand an attack of a theoretically perfect quantum computer. Or we look into specific quantum hardware, such as quantum random number generation, that then in turn can be used to generate keys for encryption and decryption. Yes, before that, I've been with the company for almost 11 years now with Volkswagen Group. Before that, I worked as a principal scientist here in the US, responsible for artificial intelligence and quantum computing. Before that, I was a chief technology officer for the Volkswagen Group Data Lab. So this is a department we set up, which right now has about 70 to 80 engineers working in machine learning, basically algorithms development along our whole value chain. Before that, I've been a consultant. That's how I joined Audi. Audi is part of Volkswagen Group, and that's how I moved over to Volkswagen Group, in case that's interesting to you. The agenda for that course is as follows. So we will talk, of course, about quantum physics in general, but fear not, there is not the whole area of quantum physics that we need to understand for being able to do quantum computing. It's only a very specific knowledge, and there is no requirement to be a quantum physicist. I know there has always been this notion that quantum physics is incomprehensible to anyone who is not a trained quantum physicist, and physicists like Richard Feynman, even in the 80s, they contributed to that notion. But I have a different opinion. I think it's just different to anything that we experience in our macroscopic and classical world. And specifically, when we talk about quantum computing, we only need to understand a very limited set of quantum physics. So what I want to say is that anyone with an interest, anyone with some mathematical knowledge can get into quantum computing, no matter if you're a computer scientist, mathematician, physicist. Of course, if you want to build quantum hardware, quantum chips, then more detailed understanding is required. But we will talk about hardware later too. So that brings me to the second important point here, which is architecture of or architectures of quantum or for quantum computers. So architecture can mean different things. Architecture can mean we talk about a quantum annealing system, which is a very special purpose quantum computer, usable or can be used for solving optimization problems and sampling tasks. And there is gate model quantum computers or universal quantum computers. These are the quantum computers that everyone wants to have and everyone is looking forward to having, but we are not there yet. I mean, we have these quantum computers, but mostly today we can use them for solving toy problems. It's not that we can do something that matters in an industrial context, for example. This is the one side of architecture. The other side of architecture is how you build qubits. So, we have bits in the classical world and quantum bits in the quantum world. So it's the smallest information unit that we use for processing. And how these bits are implemented, and we will talk about that soon too, how these bits are implemented is also something that can be referred to as architecture. Then we will talk about classical bits and qubits. So classical bits, the smallest unit of information in computer science or information theory in general, and quantum bits. So we will see there is a difference. With quantum bits, still we're interested in zeros and ones, but here we have a direct connection to physics. So that makes it somewhat more challenging to implement bits. And on the one hand side, on the other hand side, it gives us some possibilities on how to operate with on these quantum bits and on the effects that we can use, the quantum effects relevant for computation, for quantum computing. And we will learn about that too. Then I have some examples. So usually or up until 2017, I always started with a theory and then had some examples. So this year's lecture is different. After we cover some prerequisites, I will start with examples. So things that we here at Volkswagen Group implemented with quantum computers so that you have an understanding of what they can be used for in the real world. Because I know there is always this notion of quantum computers being super far out. And I just said some of the quantum computers, like gate model chips, can only be used for solving toy problems, true, today. But then there are others, like annealing systems that can be used for practical problems already. And even jumping back to gate model computers, even these gate model computers, even though you use them for solving toy problems only, you can use a real world problem or take a real world problem and scale it down until you can fit it onto the chip or use the chip somehow for processing. And then create intellectual property. So develop a new algorithm for a scaled down version of a molecule that you can simulate, and I hope that once more powerful chips are available, this algorithm also scales to these chips. We will then talk about some quantum algorithms that are standard, so basic knowledge in quantum computing, such as Deutsch's algorithm. So was one of the, or actually the first, David Deutsch, the first person to come up with an algorithm that shows the potential of quantum computers, which means he did something with a quantum computer in theory. So he didn't have one back then, but in theory, that is significantly more efficient than with a classical computer. We'll look at Shor's algorithm. Shor, I mean, you have heard about that probably. Peter Shor found an algorithm for factoring prime number or prime factorization. So this is a problem that is, on the one hand, mathematically interesting because there is no classical efficient way to solve this problem. But it's also of practical relevance. Practical relevance because a lot of the algorithms that we use today for encryption, be that RSA, be that elliptic curve algorithms, be that Diffie-Hellman, all of these have weaknesses, and RSA specifically is based on factoring, or the premise that no one can efficiently factor or find the prime factors to a big number, the key that you use for encryption. But if you can do that, then you can also conclude back to the private key and decrypt data. And that's what Peter Shor, in theory, showed is possible. So still, we don't have these machines today, but it's something we need to start thinking about because it's very difficult to predict how the development of quantum computers will progress. So I just said before, maybe in 10 years we will have these machines, but then quantum computers are also used for material science, for solving complex material science problems. And one of the weaknesses in how most of the quantum computers are implemented today is materials. Materials are not perfect, and somehow you cause bit flips. It's called, sorry, there's an error, right? So what you need is error correction. But what if I had the perfect bit? I could get rid of error correction. And getting rid of error correction would mean I need less bits and I can process more complex problems on a chip. So what I want to say is that even the development of quantum computers will be augmented or caused by new quantum computers. So developing new quantum computers will allow us to develop new quantum computers, if that makes sense. We will also have a look into searching with a quantum computer. So there is another very famous algorithm. Love Grover came up with it. It's called Grover's search algorithm. And here we're talking about an unsorted database, which can be solved in, searched in O squared of n, calls to an oracle. Let's say I have 1 million entries in a database. Then with a classical algorithm, in the worst case scenario, I would need to go through all of these entries. So that means in the worst case, I have n calls to the oracle that I need to do, which is 1 million. But for a quantum computer, Peter Shor, Love Grover showed that it's a lot more efficient. So it means he could do it with his algorithm, or we can do it now because he found it, with 1,000 calls to the oracle, which is way more efficient. And this is also a problem for public key cryptography, because in public key cryptography, we don't need to try, using a quantum algorithm to crack public key cryptography, we don't need to try out all possible combinations. So with Grover's algorithm, there is this premise that we can find the key rather efficiently, even if we use keys of, let's say, 4096 bits or so. These are still threatened by quantum machines. We'll see. And then we'll talk about, or we will do some hands-on examples, which means coding examples, both with D-Wave and gate model quantum simulators. So we will see. Maybe we can access a real quantum computer. If not, we will use simulators. Depends on how things progress. And I just have this here as an example, quantum artificial neural networks, because I feel it's one of the most interesting fields in quantum computing. So is to see where quantum computing and machine learning intersects. And there's many different things. And one of these is quantum artificial neural networks. And there is not the quantum artificial neural networks. There are many ways to use quantum computers for training or solving artificial neural networks. So that's why I thought this is a good example, but there is more. Maybe we will find time to talk in more detail about other algorithms or not. We will see how it goes. So far, so good. Let's talk about the prerequisites. So you need for quantum computing, you need a basic knowledge about quantum physics, which we will cover in this lecture. You will also need a basic knowledge about linear algebra, specifically vector spaces or complex numbers, which we will also briefly cover in this lecture. It's just, I know you had that in the past, and probably everyone knows linear algebra really well, but still we want to be on the same page and have the same understanding. That's why we will quickly go through that. If that's not interesting to you, you have the advantage of having a video lecture here, so you can just skip it. That's perfectly fine. And we will talk about Dirac notation. So it's just a different way of writing down algorithms or a vectorial representation of algorithms. So it's easier to write it in his notation. I will explain throughout that lecture what that is. It's easier to create algorithms. It's easier to create transformations. It's just, if you talk about it in a physics context, you use the Dirac notation so that you don't need to translate between spaces. So let's say I have some translation from position into momentum space. You don't need to do that with Dirac notation as you go in your calculation or computation. You can do it at the end. So you can finish your algorithm, you can produce the output in Dirac notation, and then extract the relevant result in whatever space you are. Of course, the question comes up why we don't need to have detailed or deep knowledge about quantum mechanics in quantum computing. Easy, because so as I mentioned in the beginning, there is only a few things about quantum physics we need to understand to get into quantum computing. Keep in mind that even if very good or famous computer scientists, not all of them may understand how a transistor works. Not all of them may understand how to assemble a motherboard, but still they're good computer scientists. And for us, as being good quantum computer scientists, it's also not necessary to understand everything about quantum physics. We just need to understand the things that are relevant for doing our computation, except you want to work on chips or improve the theory around these chips, then there is a deeper knowledge required, of course, but that's not covered in that lecture. The other reason for why we don't have to have a detailed understanding is that a quantum computer per se is an extremely simple physical system. That doesn't mean it's simple to build. It's very complicated to build a quantum computer, and we will talk about that in a bit. But what I want to say is that once I have my quantum computer and once I have my bits assembled, then it's extremely simple. It's discrete, it's not continuous. So imagine you have a hydrogen atom, you have a proton here, and you have an electron in an orbital around it. Then this electron can move into steps. So it cannot be or move outwards continuously. It can occupy these shells in steps, quantas. That's why it's called quantum physics. So there are other quanta that are relevant in quantum physics, but the step size is the smallest step size that you can take, and that's why it's called quantum physics. Anytime someone says they did a quantum leap, keep in mind that this is the smallest leap that anyone can ever take, so it's not at all big. Let's see, any key information left? No. Let's look into the discreteness a little more. There is one example I always like to bring up. This is not specifically relevant for quantum computing, but just should give you an understanding for why quantum physics is discrete. And here we talk about electronic quantum numbers. Quantum numbers, or electronic quantum numbers, in that case, they describe electrons quantum physically. And we see 4 of these numbers here. So we have the principal quantum number, designated by the letter n. We have the orbital angular momentum quantum number, designated by L. We have the magnetic quantum number, designated by ML. And we have the electronic spin quantum number, MS. And let's look at the principal quantum number first. So the principal quantum number designates the principal electron shell. So it can go from n equals 1, 2, 3, to whatever up. And that's how the shell or the position or where you may find the electron, the probability of where you may find the electron increases. Then we have the orbital angular momentum quantum number. This one depends on n, the principal quantum number. And so this one designates the shape of the wave function or the orbital. So here you may hear or have heard about the SPDF orbitals. Here we see an S orbital, which is the simple spherical orbital. Here we see a P orbital, which gives you this dumbbell shape, so these two. And again, this describes just the probability of finding an electron in these orbitals. So it's higher to find them here, or actually you will find them somewhere in here. Yeah? And the orbital angular momentum quantum number can take values of 0 to n minus 1. Okay. Then we have the magnetic quantum number, which describes the orientation of the shell. So imagine we want to look at that one here, this wave function, and you have 3 axes, x, y, and z. Then it can be oriented along each of these axes. So this gives me 3 possible configurations for this one here. So that means if we have for a p orbital these 3 possible configurations, that means the ML goes from -1 to 1. So it can take minus L to L. Minus L to L in that case is -1, 0, 1. So we have 3 configurations. And then there's the electron spin quantum number. And this quantum number is totally independent of all the other quantum numbers. It just describes the spin. For example, spin up, spin down. So spin at 1/2 minus 1/2. And here I have an example. So as we have seen before, all these electronic quantum numbers, except the first one, and the last one depend on others. So MS depends on ML, ML depends on L, MS doesn't depend on anything, sorry. ML depends on L, L depends on N. Yeah? So this example here says, let's assume an electron jumped from an energy level n equals 5 to an energy level n equals 3. Did an absorption or emission of a photon occur? This is something I haven't mentioned yet. So when you want to move an electron further away from the nucleus, then you need to add energy. And energy in that case is a photon. So if you add a photon of a specific energy, you can move the electron up by 1 step. If you add specific energy, you can also move it up a couple steps, not only one at once, you can move it up a couple steps. You can also kick the electron out of the shell. That's also possible, or away from the nucleus. So the answer to that question is if it jumps from n equals 5, which is further away, to n equals 3, which is closer to the nucleus, then absorption or emission occurred. It's emission. Emission because we're losing energy. Right? So we add energy to move it further away, but then if we want to get closer again to the nucleus, this energy must go up. So this is then emission. So if n equals 7, the principal quantum number, what are the possible values of L? It's the possible configurations or orientations or shapes of the wave function. What are the possible values here? We have 0 to n minus 1, which is 6. We will see on the next slide what exactly that means. It's just to get a basic understanding right now. So if n equals 3, L equals 2, what are the possible values of ML? So if we look at ML, the magnetic quantum number, we remember that it is minus L to plus L. So we have 5 possible configurations. It's -2, -1, 0, 1, 2. And we will also see on the next slide what exactly that means. For now, it's just important that you know how to calculate it, and then we'll see what it means. And the spin quantum number is independent. So I leave that as an exercise to you if you wanted to find out how many possible configurations there are. Remember, spin quantum number, as it's independent from all the other ones, means we can do all possible configurations that you see here twice, right? Because spin 1/2 and minus a half for each of these configurations, since it's independent. Let's visualize electron orbitals here. I briefly mentioned the subshells, so SPDF, that you see here, and configurations of L. L, remember, so this one designates the principal quantum number, and this one here, L, designates the shape of the orbital. So let's look at that one here. That is very interesting. So if we say that P subshell is 1, then we look at 3 possible configurations here from -1 to 1. So this is the orientation that I mentioned before on the coordinate system. We have 3 possible configurations of this subshell. So yeah, basically that's that. The D subshell, so the magnetic quantum number for L equals 2, it gets more complex. So we see different shapes here. We see 3 orbitals here and 6 possible orbital or P orbital electrons. P doesn't stand for possible, it's just the P subshell. 6 electrons that can occupy these shells. Why is it 6 in that case? So we look at that again. So remember, the spin quantum number is independent of all the other quantum numbers. So that means I can have 2 electrons in each of these shell configurations. So it means 2 here, 2 here, 2 here. It's just 6. So much to the discreteness of the quantum numbers. Discreteness is also interesting and valuable for us because we're interested in computational basis states. So again, we want to have something that's comparable to classical information theory or classical computer science. We want to have a bit, the quantum bit. And for this, we will look in a little more detail into quantum computers and how to build these in a moment. I have some news here. You may have heard about Fujitsu's digital annealing system. This is not a real quantum computer. It's just a hardware, an FPGA specifically, that emulates a quantum annealing system or aims to bring or do the same computation classically that a quantum annealing system does, which is not possible because in a quantum annealing system we use effects such as tunneling, but there are tricks how to simulate these effects classically with thermal jumps. We will learn about that in a second. So it's just interesting to look into that. So there is not only development in quantum hardware, there is also strong or a lot of development going on when it comes to quantum-inspired algorithms and quantum-inspired hardware. So in the course of learning about how to write algorithms for quantum computers, we can also learn a lot about classical algorithms and how to enhance and augment classical algorithms to make them better. What's a quantum computer? It's an extremely simple physical system that we learned that just before, but it cannot be defined as a computer that operates under the laws of quantum mechanics, because everything, as we know, operates under the laws of quantum mechanics, even this TV here, but it doesn't leverage quantum effects for computation. So what we want to make a distinction of is that a quantum computer uses quantum effects for computation, while any other computer, although it's also based on quantum mechanics, does not use these effects for computation. The other challenge is that quantum states, so that means a quantum bit, in our case, the smallest information unit, so let's only take 1, they're extremely sensitive to environmental influences. I give you an example. If you rely on superconducting qubits are implemented with superconductor, as the name says. Let's say I have a ring of metal like niobium or aluminium, and this is just an abstraction, it's more complex. But let's say I have this ring here, and I have to make it superconducting. So what I do is I cool it down. So we have to cool it down to 15 to 20 millikelvin, which is colder than space, which is 3 Kelvin. And I use this and induce current in both directions. You know, as we achieve or obtain superconductivity, there is no electrical resistance. So current can flow in both directions. It can flow in that direction and that direction. And we know moving currents generate electric fields, magnetic fields. So that means current moving in one direction, it generates me a magnetic field up, and the current moving in the other direction generates me a magnetic field down. Which can be used as a bit, our quantum bit. But these magnetic fields are very sensitive. They're so sensitive that I need to shield them from the Earth magnetic field. I cannot just operate it just in a big fridge. I also need to make sure that the Earth magnetic field does not influence my computation. Moreover, I want to make sure that I operate these systems in a vacuum. Because if I don't, let's say there's an oxygen atom flying around and that all of a sudden sits on that superconducting qubit, this will hamper my computation. It will destroy my computation. So you see, it's very difficult to isolate these systems from their environment. You want to make sure, specific terms, that you isolate a quantum computer or any quantum physical system that you want to do something with from its own irrelevant physical properties and the environment. At some point, though, you need to interact, so that's important. I have to have some environmental connection because I want to read out the results of my computation. I want to do my computation. That also requires me to have access to the system. So this is the whole artistry in building these quantum computers. I want to make sure I can access these systems, but then also isolate them from the environment. It's very complicated to build these systems. Yes, this is what I just mentioned. Qubits cannot be encoded in systems of macroscopic size because we cannot isolate them. And isolation can be achieved if, so we are talking about a small number of states in a system of atomic size, or we don't have any internal features that matter. So you don't want to, not only want to have it isolated from your environment, you also want to make sure that the internal effects that occur during the computation do not hamper with your computation. And as I said, it's difficult to design. We'll learn about that in a second. And we also learned about how to avoid decoherence. So in the case of superconducting qubits, we have a big fridge. We cool the system down. We isolate it from the Earth magnetic field. We operate it in a vacuum. And this is somewhat challenging, but possible. It's doable. And why do we do all that? This is also something I will talk about in a second, but basically, if you just look at that very simple graph, if we use a classical computer, usually what happens is that if you increase the input size, the more complex your input becomes, the more input you have, the more time you need to process it. Still, that's true with quantum computers, but it's possible to do it a lot more efficiently. So not necessarily I need the same time. And here's one thing that I want to emphasize on. Classical computers can do some things very well. Quantum computers will not replace classical computers. Quantum computers will be coprocessors, or are coprocessors. They will augment classical computers. There is no need for a quantum Internet Explorer. So we want to make sure that we keep in mind that quantum computers are coprocessors. Let's start with classical computers. And you have heard about Babbage with his analytical engine. This was, or difference engine, sorry. This was the first computer, first hardware that was built in 1822. So that's how it all started. So really a mechanical implementation of a computer that could execute computations. Then you may have heard of Ada Lovelace, who came up with the first computer algorithm. So what she did was design algorithms. Of course, she didn't have computers at hand, but she designed it and wrote it down and came up with algorithmic formulations to solve problems. Here she has one for computing Bernoulli numbers. And then another very famous person in the context of computer science to know and have heard about, you need to have heard about him, is Alan Turing. So Alan Turing came up with the Turing machine, and you know what a Turing machine is. So basically, you have an infinite band, you have a reader, and you can move that band back and forth, and you can do operations on that band. So meaning writing things down on that band. And the very interesting thing is that any algorithm can be implemented by a Turing machine. And this means that this Turing machine is a universal computer. It's sort of an architecture for a computer, a theoretic one, but still, a Turing machine is the prototype of a universal computer. So it can do anything or execute any algorithm. So with this reader here, it's not, it's a head. Let's not call it a reader. You can also erase what you've written on that band before, move backwards and forwards, and write. So that's how a Turing machine works. In theory, so this, in theory, it's fact, you can implement any algorithm by means of a Turing machine. If we look at classical computing devices, I mean, of course, you know the abacus and the transistors, silicon chips. So that's all these devices that we know and that we maybe you haven't used that one, but you probably have heard about it. So that's all these devices that we know, and then back in the 1980s, I think it was 1982 or so, there was Richard Feynman who asked a question. Or actually, he didn't really ask a question, he just gave a presentation and wanted to make sure that people understand that nature is quantum physical and that if we want to do a simulation about nature or simulate nature, then we want to make sure it's quantum physical. And that's a very interesting point because the question that came up then was, if we try to simulate quantum physics, it turns out it's very difficult for classical computers. And you can ask then, does that mean that computers using quantum effects are more powerful than classical computers? And that was the question that sparked the whole field of quantum computing. Oh yeah, Richard Feynman. Yeah, Richard Feynman kicked the whole field off. Everything from there is history. I really recommend looking into these two publications here. I mean, there is a lot more, but these two specifically that I find interesting. So the first one is from Paul Benioff from 1982, Quantum Mechanical Models of Turing Machines that Dissipate No Energy. So basically a quantum Turing machine. And here we have a publication by David Deutsch on the quantum theory and church Turing principle. David Deutsch, as I mentioned before, is one of the guys who, together with Richard Feynman, kicked the field off and who came up with the first algorithm, quantum algorithm, that showed you can do something with a quantum computer a lot more efficiently than with a classical computer. And what he did was, so if you don't need to derive the whole algorithm from that one statement here, we will learn about it in more detail later anyways and go through it with an example. But what he did was show that with a quantum computer, given some inputs, you can find out in one call if a function is constant or balanced. A constant function would produce, let's say you have only one input bit, and it can be 0 or 1, would produce, no matter what input you supply, would produce the same output, so either 1 or 0. A function that is balanced would produce different outputs for different inputs, but same amount of zeros and same amount of ones, depending on what you supply. And with a classical computer, you need at least 2 calls to figure that out, right? But with a quantum computer, you can do it in 1 call, and he showed how that works. Daniel Simon, he came up with another very interesting problem, so could be interesting for cryptography. We'll look into that too. So it's a special case of the abelian hidden subgroup problem. So he found a hidden subgroup and or can find a hidden string basically in a given set of inputs and that produce outputs. So that's very, very interesting too. Peter Shor, he's the guy who came up with the algorithm that allows us to factor or do prime factorization by means of a quantum computer. Still, this algorithm has a significant classical part, but the speed up is achieved quantumly. And so, which then, if we have a quantum computer, as I mentioned before, poses a threat to public key encryption or infrastructure. And Love Grover came up with a search. Search of a database, an unsorted database. Let's say you have a phone book and you want to find a specific entry, and you can do it in square of n calls, which is significantly faster than what you can do with any classical computer. So we always assume the worst case scenario. Of course, you could be faster, and of course, you could use a classical computer and say you have 1 million entries. And if you're very lucky, it's the first one. Well, most likely, you're not lucky. But the worst case, this is what we assume here, would be n. So 1 million calls to the phone book. There are different realizations or implementations of quantum computers when it comes to hardware. Photonic optical quantum computers, so using photons as quantum bits is one way. Quantum dots or quantum nanoparticles, so particles small enough that exhibit quantum effects. We have flux quantization. That's the quantum bits most people rely on these days, which is superconducting quantum bits, the one that we briefly mentioned before. So the ones where you have rings of, let's say, aluminum or niobium and cool them down, induce current and create two magnetic fields, which is your quantum bit. And then liquid state nuclear magnetic resonance is also something, or also a way to implement quantum computers. But right now, these ones and ion traps, in my opinion, are the most important ones. When it comes to quantum computing, I know that everyone has heard about, or people who look into quantum computing has heard about universal quantum computers, and that's usually the quantum computers we talk about. But there's also another architecture that we will go through in this lecture that is a quantum annealing system. So it's a special purpose computer. It can't solve any algorithmic problem like a gate model or universal quantum computer could do, but it can be useful for solving optimization problems and sampling tasks. And a lot of the things that we want to solve, at least in industrial context or academic context, are optimization problems. So it's one of the most important categories of problems. And here these systems can help. And it was proposed already in 1998, and some other people contributed to that too. And there's a company out there, I don't want to make any or any advertisement, but there's a company, D-Wave. These are the only commercially available quantum annealing systems out there that built that quantum computer. And there was this announcement that IBM made in December 2015, where they said, so a quantum annealing system is the simplest form of a quantum computer and not difficult to implement, and it's restrictive, and computational power says is same as classical computers. We're still trying to find out if quantum annealing systems are a lot better. So for some problems that we specifically worked on, we achieved some speed ups, but maybe there is some person out there that can find a classical algorithm that beats our algorithm. So for anything I talk here and any of the problems I introduce, if you have a better idea with a classical computer, let me know. I will not be angry because in the end we end up with a better algorithm. But it was surprising to see that one day later, Google wrote a blog post where they said, if you use one CPU and compare it to your quantum annealing system, then it is more than 10 to the 8 times faster than a classical computer. So that's also the question that we need to ask ourselves. What do you compare a quantum computer with? Is it I use one quantum chip? Do I compare it with one classical chip? Do I compare it with a cloud? Do I compare it with whatever it is specifically used for solving a problem? That's a question. So it's still an open discussion. But I feel until we really see something that a quantum computer can do that not even the best supercomputer in the world can do, then, I mean, we have seen something last year. Google made another announcement with their own quantum, their gate model chip. But until we really see something that's industrially or academically relevant, then I feel this will always be the question of how to compare it with classical computers. Still, as a company, if you look at it from that perspective, we're not only interested in problems that you cannot solve with classical computers, we're interested in problems that you can maybe solve faster with a quantum chip. So let's say I do traffic flow optimization. I look into optimizing vehicle positions based on the dynamics of the real-time traffic, and I collect position information of these vehicles every 1 to 5 seconds. Then one of the challenges is to solve the optimal distribution problem fast enough so that I can communicate back to these vehicles very quickly. If my algorithm needs 15 minutes, that doesn't do me any good. But with a classical computer, I may be able to solve it in 15 minutes. So it's still solvable. So it's not something that only a quantum computer can do. But if I do it with a quantum computer, I may be faster, and that already may give me an advantage, a business advantage. So that's the problems that we also look into, or we should be interested in, have an open discussion about. Generally, there has been, when it comes to developing technologies, generally there has been this historical, or is this historical observation, so also when it comes to development of quantum computers, that we develop a new model of a physical phenomenon, so let's say about quantum physics, and then we build some devices that employ these physical phenomena, like quantum computers. And sometimes it is that the model comes first, and sometimes the device comes first. And so this is just what I want to emphasize, and we will learn a bit more about this, because if we just extrapolate classical computers, or you know Moore's law, right? So Moore's law basically says that if so every 2 years approximately, the feature size on silicon chip doubles, which also increases or continuously increases the computational power. It's always the question, is it a self-fulfilling prophecy, or is it really a law? But up to now, it has been fairly accurate. But what if you approximate that, let's say up to 2050, then you would have to have computers that are size of an atom, or you have to engineer nuclear matter such that you can use it for computation. And while that's possible, it's really, really difficult to handle such computers. They get hot and are difficult to handle, and there must be a way out. And in that case, our way out is the quantum computer. So that's why we look into quantum computing, or into other things that will give us more computational power, because we always need more computational power. True. So again, I don't want to make any advertisement, but so in that case here, D-Wave was the first company that had a quantum computer out in the market. Now we see many other companies, so a quantum annealing system in that case. So I always want to be careful and distinguish between quantum annealing and quantum computers. It's also very important for the community. Although the D-Wave system uses quantum effects for computation, which is a quantum computer, I want to make sure that you distinguish between gate model chip and D-Wave system. So it's two different things. So we have many other companies like Microsoft, Intel, IBM, Google, many research institutions looking into quantum computing and learning about how to design these systems, learning what algorithms, what problems I may solve with these computers. That's also very interesting because it's such a new and emerging field. Even when you have a clear understanding of a problem, even when you have a quantum computer that's significantly or big enough to solve that problem, sometimes you don't know if it really does me any good for that problem. So you want to try out. It's a sort of applied research. You have a problem at hand, and you try different tools. And we won't forget that quantum computers, it's not magic, it's also a tool. If we find that this tool is the good one to use for solving a problem, well, fine. If not, we use something else. All right, so this concludes my first lecture. And the next thing we will learn about is, again, we will understand why quantum computing is interesting and why we want to look into quantum computing in more detail, and talk about quantum annealing and gate model chips, and then also about some problems. And at some point, maybe not in the next lecture, we will start or dive deeper into the theory that's needed. Thank you very much.